normal circumstances, I will be pairing, but today Alexey cannot be here, so I will be doing it alone. I will try to do his part also. So first of all, I would like to introduce myself. My name is Kevin. I'm a software consultant at Thoughtworks. Okay. Alexey, the person I got here, is a software architect at AutoScout24. And the thing is, I would like to be transparent on what are we going to share, because Kafka Streams and architecture is a really huge topic. So we skipped some really cool things because we don't have enough time. And it was a really complex decision to see what I'm going to explain or not. First of all, you will meet Scoutworks. It's the relationship between AutoScout and Thoughtworks. The business requirements that we needed to satisfy and why we did this architecture. A brief introduction to some Kafka and Kafka Streams conventions, not everything, because actually they're huge, but just the important things for this talk. How we brainstorm and design our architecture, and talk about some resilience and operations on this kind of architectures. A brief introduction to what we are working on. AutoScout is a classified platform with a lot of people selling cars there and buying cars and whatever. There are a lot of numbers, like we have 2.5 million listings, 3 billion page impressions per month. That's a lot of traffic, actually. But our current domain on AutoScout is the listing. The listing is whatever you see on the web page with a description of a car. We found that images actually are really important on listings, so they have a special treatment. And dealers is the person that wants to sell something to customers. What we are building is a product that lets dealers to export those listings to other platforms, to other partners, just to improve the visibility of ads and then be more able to sell those cars. And we had, as always, a set of business requirements. First, a dealer should be able to roll in or roll off from that system. It's not mandatory. All listings that are active will be exported, and listings that we remove from our platform or hide them should be also hide on other marketplaces. Actually, more business requirements is that we at least need to have everything on other platforms, but not the latest information. So we had some tricks to do. And the listing data format is highly dynamic because AutoScout is working on different countries where cars have different information. There are different extras depending on the country, different field, different things. So we needed to be able to reprocess depending on the source or on the origin of the listing. And that was really important because it's part of the business. Technical requirements. We don't always have the same load. As always, there's some load, some noise during the day and during the night, and there are some spikes. It should be easy to add other partners to export to other marketplaces, and it should be easy to monitor and trace. So what we have right now in AutoScout, we have two systems. Let me just point here. We have a read-write system with an oracle. That will be what we call cache tag. It's a normal application that have different services that write and read the same oracle schema. And then we have a pipeline that exports this data to a new architecture that we're building. It's a read-only data flow on a single direction. And we thought that the best fit for that was Kafka, of course. Why not? So I'm going to explain a little bit an introduction to Kafka. Probably everybody knows a little bit of Kafka. Maybe you heard about that. It's a streaming platform where you have records that you push them on a stream, and then they go to another site. Records are in topics, and those topics are formed by partitions. Partitions is like a structure that is a sequence, it's an ordered sequence. Each partition from client side is append only, so you can only append data. You cannot remove or modify data that is already there. Records have a partition key to know in which partition we should write that record, a value, and a timestamp. Timestamp is the moment where the message has been produced. And Kafka has some guarantees, actually, in how it works. Kafka ensures sharding on different partitions, so that means that data will be eventually be distributed across the cluster. This replication depends on the configuration of the broker, that actually is quite complex. Kafka guarantees the order of records on a single partition. That means that the order that Kafka receives those records will be the order that consumers will read those records. And at least we will receive those records on our consumers. At least once means that we can have duplicates, but we will at least receive the message once, but more than once. So Kafka is often used for real-time streaming applications, and what we are building right now is a streaming application. So how listings change and move around our system fits very well on how Kafka works. We can always go back and reprocess the entire topic. I don't know if you have seen that replay process in Kafka, that you can just replay everything from the beginning. And this is probably the main point of why we choose Kafka, is that it enables developers to choose, to design software, design an architecture that is built using functions, like in functional programming. It's a library or a framework that is really opinionated. It's a Java framework, actually. It provides the possibility to build elastic, scalable, fault-tolerant solutions. Uses Kafka to store everything, actually. So if the application fails or you need to redeploy, you will just read from the beginning on Kafka, depending on your configuration. And supports different processing actions like mapping, aggregating, and streams of data. And Kafka has really strong capabilities on resilience. So sometimes it will even sacrifice some performance on some consistency just for resilience. So it's cool. If you run your own Kafka cluster in a cloud provider, it's a good idea to at least have 3 or 4 nodes in different availability zones to ensure that if there is one problem in an availability zone, it will continue working. Kafka Streams saves everything in Kafka. It means that on different configurations, Kafka Streams can replay and restore the data. If you have only one node, on one Kafka Streams node, everything will stop if the application is down. It depends on the strategy that you have. You can have stateless processors. That it means it will continue working because you don't have any state, so you can just process everything that it's coming on. So the simplest setup, and the one that we are using, is we just wait until we reprocess everything, and then we continue receiving records. How can we use Kafka conventions to model with functions? How to make our architecture simpler and easy to evolve. So this is a function, actually. It's a function that maps any shape to a circle. And functions, as they are, have some interesting properties. Without going too deep into mathematical concepts, functions are really suitable to build systems because they are atomic. A function runs once and completely and cannot be interrupted. Functions that are pure, actually. So if you have a function that gets some data and writes some data, that's fine. As functions are transactional, it's really difficult to build distributed transactions. So using functions as your system instead of services forbids you, or at least makes it really difficult to build distributed transactions. Functions can be composed as objects. You can delegate some logic to other objects. In functions, you can delegate some business logic to other functions. And they are state ignorant. It means that you don't know where the state is coming from. In that case, when I mean state ignorant, it doesn't mean that they don't have a state. Actually, functions are stateful sometimes, but they don't know where the state comes from, even if it's from the beginning or from the end of the function. How do you model an architecture with guarantee some consistency if you only have functions? The thing is that we cannot think in functions right now without thinking in Kafka, because it's our backend in our architecture. And functions are just logic. So a function is just an algorithm that gets some input from somewhere and just writes some output in a topic. So we need to rely on Kafka for that consistency. Kafka only ensures consistency in a single partition. It means that if you have 2 records on different partitions, you cannot guarantee the order or the consistency between those records. And it's degraded when Kafka starts a process that is called repartitioning. Repartitioning is a process where all records from one partition are processed and sent to another partition. This is an example of repartitioning. This is actually happening to us. So let's assume that we have a dealer that contains a stock of listings, 5, 10 listings, 10 cards that they want to sell. Each listing has an ID, and what we want to do is get the information from the dealer where they want to export those listings, put them on the listing, and send the listing across the system. So we have, at the end, a listing with all the export targets, all the marketplaces that where we want to export to. In our case, we are the partition, because we want to guarantee the consistency by dealer, the partition will be by dealer ID. But for listings, the partition is by listing ID, because we are sending listings. And actually, we are also sending more than one message, because a dealer can have actually more than one listing. Actually, the stock will be like hundreds of listings. There's a fun fact on Kafka Streams, actually, that if you're repartitioning and you have more than one instance of a service, you can start consuming messages from one instance and at the end produce the message on another instance. Because when you repartition, you are saving this information again on Kafka, and then it could be another consumer that is getting this information, finishing the processing of it, and then pushing it to the next topic. And we found actually that Kafka partitions and conventions are really close to some domain-driven design patterns and concepts. For example, in domain-driven design, an aggregate root is the transactional boundary of a business entity. So in DDD, they say you can only guarantee the consistency of data for a single aggregate root. And an aggregate root for Kafka is just a set of records in a topic for the same partition key. It's important because they are ordered and transactional, and those are the properties of actually aggregate roots from a technical point of view. And moving to a more practical scenario, our current project. This is the first function in our current architectural diagram that we built with some stickies. Arrows are the data flow of our system. We have 2 AWS lambdas that push some information to Kafka, depending on some business use case, like adding new exports, and re-exporting the dealer stock for errors and so on. And then we have a service, the yellow sticky, that represents the export function. This service is responsible of generating a message per each listing that needs to be exported for a single dealer, with the information about where to export and how. Then we have the enrich function that is implemented with a service called export listing enricher that pulls information from listings, images, and export targets for a given listing, merge them, and then pushes the duplicated records to the next topic. And finally, we have the send function implemented by another service. And it's an edge service. It's not written in Kafka Streams. On the learnings, I will share why we didn't use Kafka Streams for this part. After looking at that diagram, after some time, we found that our system was built using the same set of tools that we were using for designing software on a more low-level perspective. And that was a really big win because we could reuse a lot of design knowledge that we already had. So we already work with functions, so why we cannot use functions for other bigger concepts. This is a brainstorm of the enrich function, the second that we said, where we are merging different topics. And as you can see, arrows are the data flow. The actual implementation is a composition of functions. And if you notice, purple or pink stickies are data structures, arrows are functions, orange stickies are inputs and outputs, are the side effects. And those are handled by Kafka Streams, actually. So now we focus on the green part. A service can be a composition of those units over Kafka. So those are different services that are composed. In this image, both yellow stickies are services. From the client perspective, I/O on a service is atomic. It means that whenever it gets data, you output data, wherever it happens inside. And it's state ignorant because it doesn't depend on the state of the first service nor the second. It just depends on the output. And that's actually really important because on different microservices architectures, you have some service that orchestrates business logic and gets data from other inputs. Like we are doing 3 or 4 HTTP requests to grab everything, and then we manipulate this data and get an output. We don't have any orchestrators here. We just have functions that pull the data that they need. They are completely alone, they're encapsulated. They are owner of their own time, runtime actually. Summarizing up, they are atomic. You have one input and one output always. They can be composed. We have a composition of 2 functions, of 2 services. And they are state ignorant. So as before, they share the same properties as functions. So they are functions. And then we have systems that are a composition of services. Our product, that is just exporting listings from one platform to another, is a system. It has 3 services. And then we realize that systems are that composition of services, and services are just composition of functions or units. And the result of composing functions is also a function for property. So it simplified, after a long time, our architecture a lot. And we started using patterns that we already know, but we didn't realize that were useful before. First of all, there is a common pattern on functional languages. That is to, in Haskell, for example, it's a strongly typed programming language, functional language, that you decide your application is just a composition of functions with strongly typed inputs and outputs. And you need to adapt the input and output to the real world. Like usually it's a JSON or it's a string, it's a XML or whatever. So you adapt the input, then pass it to a secure composition of functions, and then output there. So we had a lot of learnings from this architecture, a lot of learnings. If you see as functions everything, the signature should be unique, because the signature is actually the contract of the function. So it doesn't make any sense for us to have functions that have the same contract, because it means that they are doing the same thing. And functions do not pertain to a single domain, but map 2 domains. And actually, this was also really difficult to find out, because usually domains are related to data, to structures, to aggregate roots. Aggregate roots is a data structure, but yeah, it has some methods, but the aggregate root is the data structure and the consistency of that. And the consistency boundary is a partition or an aggregate root, so you don't have access to everything on the system. When you receive your record on the function, you only have access to that function, that's all. So you cannot go to a database, get everything from there, and manipulate. You need to always scope your design to just a single function and a single record. Designing a system as a function composition makes everything simpler, because we are already used to design our own application with those tools. So we already design applications with functions. So designing systems and architecture with functions makes sense and is easy. Testing can be easy. Can be easy if we design tests to check outputs from inputs. The thing is that now we have power functions that are composed with Kafka, and we can always do some functional tests that grab input and produce output, and we can check this. And we also start adding correlation IDs. I don't know if you have heard that concept before. A correlation ID is an ID, a unique ID per message on a topic. So when you, on your logs, write the correlation ID for each record, you can see the whole path of your message where it had happened. And Kafka Streams should not be used for external I/O. So if you are doing HTTP requests to another service, don't use Kafka Streams. Kafka Streams is really performant for CPU-bound services. It's really fast, but it uses 1 thread per partition in Kafka. So if you do HTTP requests, you will block the entire thread, and it will kill the application eventually. Learning Kafka Streams is hard, really hard, because when you see the code, you say, oh, it's just map, it's aggregate, it's reduce. Oh, we already know that, no? It's just, we already did that on lists, on streams, or whatever language you use. But no. Kafka Streams conventions are tricky. really tricky. The differences between aggregation, reduce, key tables, a lot of things. There are a lot of different things that make Kafka streams really difficult to learn. And Kafka and Kafka streams for medium-sized messages, like 50 kilobytes, we had several problems. Like, we almost killed the broker. So the thing is that Kafka streams will write everything to disk. If you have really big records, you can kill Kafka. So you need to optimize the configuration of the broker and the configuration of the consumer and producer to not break it, enable a lot of different configurations about compressing data in memory. If not, it won't work directly. It won't work. Using Kafka streams enables back pressure. Back pressure is a pattern where the pace of producing messages, actually of consuming messages, is the same pace that you have producing messages. So if you have a system that is slow producing because you have a lot of load, you will start consuming more slower. And single duration data flows is a mindset that needs to be learned and improved. It's really difficult. Actually, on that point, people that work on front end is easier for them because they already have Flux and Redux that are architectures that are single data flow architectures. And in backend, actually, at least I'm not used to it. I need to learn it on the hard way. But when you get the mindset, actually, it's quite useful and easy to follow on. And that's all. Question? Thank you.